Hello, everyone. So we're going to go into the first session of the afternoon, and this session is on economics. We'll be starting out with Hao Chung has a presentation on foundations of transaction fee mechanism design.
Okay, thanks for the introduction. I'm really happy to be here to share our research result on transaction fee mechanism on blockchain. This is joining work with my advisor, Elaine. So first of all, what is transaction fee mechanism? So on blockchains, we have two kinds of players, miners and users. Miners' job is just to maintain the blockchain, and users, just like us, I want to send you 1 Bitcoin, you want to send me 5 Ethers, or we want to deploy some transaction fee on chain, we are users. And the transaction fee is what miners reward for maintaining the blockchain. Okay, so now is the problem. How much should each user pay? So let's think about a case. So now we have 5 users, but now each block can only contain 3 transactions. So what should each user pay actually also decides how do we allocate the block space efficiently. So let's see. What would you do if we only have a few items but lots of potential buyers? We do an auction. So you can think of the transaction fee mechanism as an auction. But now, what we want to sell is k identical items, which is the block space. And what mechanism do is to decide which user are confirmed and how much should each user pay. So this is the transaction fee mechanism. Okay, so let's check what is the problem for the current mechanism. So currently, Bitcoin uses the pay your bit mechanism. So how does it work? So let's say K is the block size. So on Bitcoin, the miner will choose the top K bits in the mempool and put it into the block. And all of them are confirmed. And each user just need to pay what it bids. And all the payment goes to the miner. That's it, easy. But what's the problem? If you use this pay your bid mechanism, it actually encourages users to bid untruthfully. So let's say if your true value for your transaction, let's say, is $2, are you going to bid $2? Not necessarily. You will try to monitor the market, and you just try to bid the bare minimum that you can get into the block. So if most of people just bid, say, like $1, why am I going to bid $2? I can just bid like 1.1, just try to get in. So this is actually really annoying for the user. User need to monitor the networks, and sometimes user also get regret because, I can just bid $1 to get in, why do I bid $2? So from the perspective of the user experience, this pay your bid mechanism is not good. So can we do better? The answer is yes. Actually, the traditional auction theory tells us that we can use the second price auction. So second price auction is like everyone in the block just need to pay the lowest bid in the block. So for example, now let's say the block size is 5. Everyone here only need to pay the lowest bid in the block, which is $3. And in this case, no one wants to bid truthfully. The optimal strategy for every user is to always bid truthfully. You don't need to monitor the network. It's easy to use. However, this golden standard design in the traditional auction fails in the blockchain settings. So because blockchain is a decentralized system, so now the auctioneer here, which is the miners, is also a strategic user. Is also a strategic players. So that means if we use the second price auction, miner can just inject the bids here, and everyone needs to pay more. So if I'm miner, I'm happy because I earn more. And in addition, miner can also collude with the lowest bid says that, oh, please don't bid $3, please bid $5. And we can share the profit of table. So from the discussion above, we can conclude 3 desired properties that we want for a transaction fee mechanism. The first one is called UIC, User Incentive Compatibility. It says that if you are a user, the best strategy for you is to always bid truthfully. You don't need to monitor the network. You just need to disclose your true value. So it is easy to use. The second probability is called MIC. That means if you're a miner, you never want to deviate the mechanism. And third property is called cyclotrip proofness, which is parameterized by a number C. So that means if you're a miner, you collude with like at most C users, your joint utility should not increase by deviating from the mechanism. And here, the second and the third property is actually the new challenge in the decentralized settings. Because now the auctioneer, the miner, is also a strategic player. And actually, so far, several works that try to propose different kinds of fee mechanism, but actually all of them fail to satisfy all 3 properties. So in last year, in Tim Roughgarden's paper, he asked the following questions. Can we have a dream mechanism that satisfies all 3 properties? So this is the central questions that we're going to answer today. But before answering the question, let's check the state of the art. So actually, Ethereum already did a really great job. So let me quickly go through what is Ethereum current mechanism. I'll just give you a really high-level introductions, and we will hide all the details, which is immaterial to the talk today. So on Ethereum, every block, there is a base fee. Only the transaction that is higher than the base fee can be included in the block. And all the base fees are burnt. That means they are totally eliminated from the circulations. But in addition to the base fee, each user can also specify tips, and those tips will go to the miner. So Tim Roughgarden actually shows that if the network is uncongested, that means the demand is larger than the supply, then the mechanism will behave like the posted price auctions. Then that means every bid higher than the posted price R, which is the base fee, are confirmed and they pay R. Miner gets nothing, everything is burned, and in this case, we are fine. It actually satisfies all 3 properties. However, if the network is congested, that means the demand is larger than the supply. So let's think of there is a burst of the demand that allows the user try to compete with a limited block size. In this case, each user will compete with each other by bidding tips. And in this case, the mechanism will just reduce to the first price auctions like Bitcoin. And as we have seen, it doesn't satisfy UIC. So now, go back to our question. Can we have a dream mechanism that satisfies all 3 properties? Unfortunately, the answer is no. So in our paper, we show that if the block size is finite, then no non-trivial mechanism can satisfy UIC and 1 SCP at the same time. So here, non-trivial mechanism means the only mechanism that satisfies UIC and 1 SCP is to always reject everyone. But that makes the blockchain useless. And moreover, our impossibility says if you want UIC, you cannot have one SCP. And one SCP means this is a coalition formed by one miner and one user, and this is actually the weakest coalition we can conceive. So that means if you want if you want UIC, you cannot even resist the weakest coalition. And actually, to prove this impossibility, we prove this key lemma first. So this key lemma says, no matter the block size is finite or infinite, if you want UIC and one SCP, miner must get nothing. So this key lemma actually says that on Ethereum, we just saw that everything will be burned, all the base fee will be burned. This is actually necessary in EIP 1559. Okay, so it sounds like a dead end. Oh, we cannot have a dream mechanism. But our paper also gives a possibility result. So the problem is, how do we bypass the aforementioned impossibility? So the key observation is, maybe the adversary we consider is too strong. So in the impossibility proof, we assume that the coalition can overbid for free. Okay, what does that mean? So let's use the second price auctions as an example. So if you use the second price auction, everyone pays the lowest bid in the block. The miner can conclude with the lowest user and ask the lowest user, can you bid 5 instead of 3? We can split the profit of table. And the lowest bid user says, of course, we can do that. Because whatever, I'm not going to be confirmed, so it doesn't matter I bid 3 or I bid 5. However, blockchain is a repeated auction. There's always another block after this block. So suppose your true value is $3. You are not confirmed for now. You may be confirmed in the future, and it's possible for you, you need to pay $5 in the future. So that means your true value is only 3, you overbid for now, and you may need to pay $5 in the future. That means you actually lose $2. So we call this model weak incentive compatibility. That means if we also consider this potential cost for the coalition, this is a weaker adversary. In this case, we can have a mechanism. So to be more precisely, by the potential cost, I mean for the user, the cost for you is the actual bid minus your true value. So in the previous example, that is 5 minus 3, which is 2. And if you are the miner, you inject the bid by yourself because what the bid you inject has no intrinsic value. So the bid is exactly the cost for you. So in this case, miner and user's utility change. They have an additional cost here. So in this model, we introduce the following mechanism. We call it burning second price auction. So here, K is the block size, and T is the parameter that you can choose. So the T is the number of confirmed transactions in the block. So that means not every transaction in a block is confirmed. So some of them just there for designing the price. So in this, so for example, let's say K is 6, T is 3. So that means the only top 3 bids are confirmed. And here, all of them just need to pay the T plus 1 price, which is the 5 here. And the miner gets T plus 1 to K's price. So in this case, it's 3 plus 4 plus 5, which is 12. And we show that the burning second price auctions satisfy all 3 properties in the weaker model. Okay, so due to the time constraints, let me quickly explain what's more in our paper. So in our paper, we actually consider the more general models. So what I just said is like the coalition need to pay the entire difference between the bits and the true value if you overbid. But maybe the adversary can learn from the historical data. Maybe if my true value is 3, I bid 5. Maybe on average, I only need to pay $4. So we have a knob between 0 and 1. That is the ratio between the difference between your bids and your true value. If the ratio is 0, that means there is no cost. If the ratio is 1, that means you have to pay the full cost. And we consider any ratio between 0 and 1. And the second one is the mechanism I just showed you only achieve one SCP. That means it only resists one miner, one user coalition. But in our paper, we introduce a generalized mechanism allow you to resist more general, larger coalition. But we also shows that if you want to resist more than two user coalition, then using randomness is also necessary. And the third one is, as we have seen, in the burning second price auctions, not every bids in the block are confirmed. So for example, we only confirm the top 3 bids there. So that means we need to put some bids there, which is unconfirmed. That wastes some block space. But we show that to contain some unconfirmed transactions in the block is also necessary. Okay, so let me quickly mention 2 interesting future directions. So in our paper, we give a first trial that we may bypass the impossibility by consider a weaker model. So can we have other models that can also bypass the impossibilities? And the second question is, I found that the mechanism design on blockchains is very interesting because it actually lies in the intersections of the cryptography and the game theory. So maybe we can use some cryptography primitives to help us bypass the impossibilities. Okay, so here's my talk, and you can find our paper on arXiv. Thank you so much.
Thanks, Al. We have time for a couple questions if you'll line up at the microphones there and there. I have one question to start with. So does your cost of overbidding or cost of cheating assume that the transaction will always be valid in future blocks? So there's no way to make the transaction, to retract the transaction or to make it, or for it to just be limited to be included in one block? Sorry?
Like retrieve the transaction?
Yeah, or have a transaction that expires after the current block, so it's no longer valid after this block.
Yeah, we indeed made that assumptions. Yeah. So that means if some chain you can retrieve the transactions, then we go back to the impossibility case.
So does this hold if I were to do like aggregate fees? So say Ethereum's case, like over epoch, right? So over the 6 minutes, would these same results hold if you aggregated fees and then doled them out in some way? So it seems like this whole mechanism is based on like the proof of work thing where you make a block and you have exclusive control over assigning the fee mechanism. But if I have multiple participants in like the same fee pool, right? And so when I mine a block, I can gather the fees, but then I have to put them in a pool because I don't get to grab them. And at the end of the epoch, there's some mechanism to distribute them. Would these same results hold?
I'm sorry, I didn't get the question.
It's okay, we can talk offline. Thanks.
Oh, okay.
Hi, thanks for a very impressive talk. And my question is that in the real market, I just want to know how can a user determine his new value, his intrinsic value to bid in the transaction fee market? Because I think currently most of the users they decide their they decide their gas fee based on the market price. So is there a way like to allow users to find their real true values in the bidding?
Okay, so is your question is that how do each user decide their true value?
Yeah.
Okay, so I would say that this is a simplified model. So we assume that each user knows their true values. So like in the economical models, you can think of like true value is the maximum price you are willing to pay. So for example, here's a bottle of water. If I sell you like $1 USD, you want to, okay, you are happy to buy it. 1.9, you are happy to buy it, but $2 you are not, then you won't buy it. And in this case, we can say that 1.9 or 2 is your true value. It's at the maximum price you are willing to pay. If it exceeds it, you are not going to buy it.
Yeah, but I think it's kind of like decided by the market, right? So if one bottle of water just costs $0.5 in all the world everywhere, then everyone will be only willing to pay $0.5 for that water. But if the water is like $1 everywhere in the world, then everyone will be only willing to pay $1, right? So I just want to mean that there is a very hard way to decide the true values, because in the blockchain market there's always like a bidding. You can only decide by like the network congestion ratio, right? Something like that.
Yeah, I agree that in practice, it's really difficult to say that what is the true value for each users, and user will also like try to observe what is the market price to decide what is my true value that is true. But I would say like if the mechanism satisfies the three properties, MIC, UIC, then that means your optimal strategy is easy. So for example, let's say you observe the market and say, okay, maybe a bottle of water just worth like $1, and I'm happy to pay $1. And in this case, you can think of, okay, $1 is my true value, and I just bid $1, and it's guaranteed to be optimal. I don't need to monitor let's say monitor the network continuously. I just bid $1, and I can leave. It's guaranteed to be optimal.
Okay.
So I will say that if the mechanism satisfies those properties, that will be easy to use. And if you are a strategic player, you try to attack the system, you cannot like gain any extra benefit from it.
Okay, thanks.
Yeah.
Thank you, Hao. Thanks. Next up, we will have Kushal Babel to talk about Clockwork Finance for automated analysis of economic security of smart contracts. I should. Okay.
Hi, today I'm going to talk about our work titled Clockwork Finance, Automated Analysis of Economic Security in Smart Contracts. This is joint work with Phil Diane, Mahimna Kelkar, and Ari Jules at Cornell University. So recent years have seen meteoric rise of DeFi, with these DeFi applications handling billions of dollars. And this meteoric rise has been facilitated by innovations in smart contracts. These smart contracts really execute like clockwork. What I mean by that? The smart contracts execute in sequential and atomic transactions. This execution is deterministic, and most blockchains have transparent execution of these smart contracts. Therefore, this has enabled easy interoperability between the smart contracts and also has enabled to build novel financial instruments. you often see this notion of money Legos, where DeFi applications smoothly interact with each other, and this interaction, admittedly, has been increasingly more and more complex. Now, I just want to focus on one application, not even the interaction of multiple applications, and want to highlight how it causes unintended behavior that was not originally envisioned in these applications. So consider a decentralized exchange application with which a user is interacting. The user wants to swap some US dollars into ETH. This decentralized exchange is obviously running on smart contracts, and the behavior dictates that whenever the user wants to buy ETH, the price of ETH would increase on their DEX. Now, any miner that's observing this transaction can actually front-run this transaction. So the miner buys the ETH before the user, and then they flips back and sells the ETH after the user. Because the user's transaction increased the price of ETH, the miner actually, using this sandwich attack, profits off the user. Here I have some symbolic variables, as in swap x and swap y. That will become more clear. The actual profit by the miner actually depends on what values these x and y take. This is captured by the notion of the umbrella term called MEV, which is miner extractable value or maximal extractable value. This is roughly the value that a miner can extract by reordering, censoring, or inserting new transactions. Now, as I mentioned, the contract composition has been really on the rise, and these interactions have been more and more complex. Some of the examples are interactions of flash loans with decentralized exchanges, lending contracts using decentralized exchanges as like price oracles to basically price their debts, flash loans with governance contracts. So most of the governance contracts require you to stake some capital, and flash loans make it easier to acquire that capital. And of course, the composition of a lot of decentralized exchanges as well. So this complex interaction of smart contracts actually leads to unintended behaviors, not just in one contract, but because of this interaction. There has been lots of hacks that you see in the news regularly. This is just some screenshots from the past few months of millions of dollars being drained because we do not really understand how these interactions happen. These attacks range anywhere from oracle manipulation attacks, as I talked about the oracle prices in a lending contract, to interactions of flash loans with other applications. There's actually an industry around this entire unintended behavior, and this figure really captures the rise of that industry. So far, there has been at least $600 million being extracted through this unintended behavior. And really, this is only the tip of the iceberg. The actual MEV estimate is considerably orders of magnitudes higher than this figure. So in order to study this behavior and study MEV rigorously, the existing techniques for studying security really fall insufficient. These techniques can range anywhere from manual human auditing to fuzz testing, static analysis of your code for like vulnerable patterns in the code, and formal verification of the functional correctness of the application. However, the common theme among these techniques is all of them focus on either bug hunting or functional correctness of the program, or like some secret leakage, like leakage of some private secret key. In this work, we go beyond this notion of security and directly reason about the economic behavior of these applications and their interactions by leveraging existing techniques of formal verification, which were earlier just used for functional correctness. And note that unlike traditional finance, DeFi applications run on these smart contracts, which are deterministic, sequential, atomic, and transparent. This allows for formal verification of their behavior. The traditional finance instruments are typically opaque, not even deterministic, let alone transparent. So benefits to the ecosystem because of our work are several folds to different players in the ecosystem. First, developers can actually prove bounds on the MEV that's exposed by their contracts and the interaction of their contracts with other contracts. Users can use this work to actually analyze the MEV that's extractable from the transactions that they're about to make. And of course, consensus researchers are also interested in MEV, and this framework provides them to study MEV rigorously because MEV actually destabilizes consensus as well. Here's the outline for the rest of the talk. I'm first going to talk about some of the definitional tools, and then I'm going to talk about the practical instantiation of these definitions into something that we call Clockwork Finance Framework. Now, on to the definitions. Believe it or not, there was not even a definition of MEV before we defined it in our paper. So I'm going to talk about the MEV definition and what it means to have secure composition. So minor extractable value definition is basically parameterized on a starting state S and player balances, especially we are considered with the balance of the miner. Now the miner can produce any valid block and gain some profit in the process. So the green bars adjacent to the piggy banks represent the balance of the miner. And MEV is the maximum value that you can gain from producing such valid blocks. Now this definition can be generalized to any player and any number of blocks that you can produce on top of the state S. So any player P that gains some profit in the sequence of valid blocks B1, B2, B3 here, extracts some profit, and this definition is formally specified in our paper where we define action spaces of the players and how much balance increment they have during this sequence of blocks. And extractable value here is the maximum profit that you can get from any sequence of valid blocks. Now note that for our purposes, rather than reasoning about any player P, it's actually sufficient to just reason about the miners. Because in some sense, miners are the most powerful actors in the system. They control the ordering of the transactions, which transactions get included in the blocks. So it's really enough to just reason about minor extractable value, and in some sense, it subsumes all the other attacks. So now that we know how we measure economic security in terms of MEV, now we define what it means for contracts to compose securely. So as before, you start from a state S, and you get some MEV by producing some valid blocks. And if you have a new contract C, then you have a new state S prime that is basically S included with the contract C. And the MEV that you can extract from the new state S prime, if that is more than the MEV that you were able to extract without this contract in the original state, then we say that the new contract C actually composes securely with the original state. And if you can extract more MEV, then we say it doesn't compose securely. There are more parameters in this definition. I would encourage you to look in the paper for formal definition. Now that we have these definitions of what it means to have economic security and what it means to have secure composition, I'm going to talk about how we use these definitions to implement a practical tool for proving these bounds on MEV. So I'm first going to talk about the design of the tool. Then I'm going to talk about how we use them for proofs and also for finding attacks. So just to start with a brief overview of formal verification at a high level, consider the program that's represented by this abstract syntax tree, where you start from a state S, and you want to verify the property blue, right? What we want is that this property holds in all the end states of the program. So there are 3 end states of the program, and if all those states satisfy this property, then the formal verification should give you a proof of the property being held in all these end states. However, if one of these end states actually violates your property, then formal verification actually gives you a counterexample, which is a trace from your program. So it's a concrete trace for a concrete execution of the program path. So analogous to this small example that I showed you for formal verification, Clockwork Finance Framework is instantiated similarly. So we start from a blockchain state S, which has certain contracts in it and certain balances of the players. Given some symbolic transactions, so by symbolic transactions, I mean that these transactions can actually be parameterized on some input variables. So suppose transaction 2 and 3 are user transactions, which are concrete. Transaction 1 could be transaction inserted by the miner, which says, I want to swap X ETH for Y USD. There are some preconditions on X and Y, namely X and Y should be greater than 0. And now we want to verify the property that MEV is less than some bound delta. what is happening under the hood behind the Clockwork Finance framework is it's basically reasoning about all the paths, which means all the reorderings of these transactions. And then it says that whether the MEV on each of these paths, if that's less than delta, then I would give you a proof. If it's not less than delta, for example, in the first path where you execute transaction 1, 2, and 3, it will actually give you a counterexample trace. And in some sense, that's like an MEV strategy. In order to do this formal verification, we leverage existing tools. As I said before, we use K-framework, which basically gives you all these tools that are highlighted here for free if you provide a language definition for it. So we provide the language definition that's in the yellow box, and then we get parsers, compilers, verifiers for the program that are written in those languages for free. Some more nice things about this framework are it has human-readable specifications of these languages, and also Ethereum virtual machine specification has been specified formally in the language of the framework, which is the K language. Now, all that remains for us to actually define this language, and then we can make use of all the nice properties of K framework. So the CFF language model consists of first the codified CF definitions of what it means to have some MEV after some transaction execution, and what it means to have secure composition. Second, we of course need the smart contracts that we are analyzing. And third, we need the EVM semantics to actually execute transactions on those smart contracts. Once you specified this language definition, you give it to the verifier, and the verifier will either give you a proof that the MEV is less than some bound, or it will give you a counterexample. Now, in order to make this practical, because in order to reason about all these paths through complex smart contract execution, we need to do some simplification for the smart contract code. So we replace the smart contract code with something that we call CFF models. These CFF models are in some sense simplifications of the smart contract code, albeit with some properties that I'm going to describe now. So the CFF models are really over approximations of smart contract code. What that means is any path that you have in the smart contract code also exists in CFF models, but the converse may not be true. What that means is CFF models, when you execute this Clockwork Finance framework with CFF models rather than smart contract code, there might be some paths, namely the third path here, which actually gives you MEV because all the paths are here, but it might not be actually realizable because we did some simplifications, and this path actually does not exist in smart contract. So in some sense, this is really a false positive, and there are no false negatives. Now, how do we do this simplification? The simplification process is largely manual, although we give some hints in the paper as to how you can automate this translation. If the contract has been already formally verified, you can actually simplify this process of manual translation. So this is this code for Uniswap v1, where you're swapping some ETH to token. Now, notice that this smart contract code has a bunch of things. First, it has some things like deadlines about your transactions that we don't really care about for our MEV analysis. So we cross that off. We prune that path. It has some limitations on how many tokens you need to buy at a minimum. We don't really care about those, because these really increase the number of paths that you need to explore through smart contract. What we really care about is the core functionality of the contract. And because of pruning of these paths, we obtain the simplified CFF models. We also open source some CFF models for Uniswap v1, Uniswap v2, MakerDAO, flash loans, airdrops. As I mentioned, CFF models actually introduce some false positives, but these false positives are easy to prune away because they really give you a counter-example strategy of MEV. So whatever false positives that you get of the MEV strategies, you can actually run them on an archive node and prune out all those false positives. And finally, what you have after this validation are actual strategies that you can execute. There are more scaling optimizations for making CFF practical. These optimizations can be categorized into two categories. The first one is the general optimizations, and the second one is contract-specific optimizations. So the first general optimization that we do is the transaction. You don't really need to reorder all the transactions, because transactions for a sender should really be serialized by the nonces of the sender. So in some sense, if you explore all the reorderings, most of them would be invalid orderings. Second, the contracts that do not really interact with each other, you can consider them as generating equivalent reorderings. And the third, in practice, we observe that if you randomize your exploration of these reorderings, it actually gives you much better convergence or much better speed up in finding higher and higher values of MEV. And for Uniswap-like AMMs, it's generally known that reordering these transactions gives you the same final state. That means it's actually path independent, so you don't really need to explore all the reorderings. Now on to evaluation of CFF on real-world data. This graph represents the 7-day moving average of MEV per block in different AMMs. We take 1,000 random samples in each month and measure the MEV. And the MEV is largely very spiky in nature, but roughly it has the value of roughly around 0.4 ETH per block. We also have evaluations for compositions. So in this experiment, we slot in the Uniswap price for the Maker Oracle price. Although Maker uses some other price methods, but this is an experiment to illustrate composability. Here we again run CFF on historical data and plot the highest observed MEV blocks when you actually use Uniswap as the Oracle price in Maker. Just to give an intuition of why this composition experiment is important, if you use Uniswap price in Maker, you can actually manipulate the Uniswap price and then liquidate some positions on MakerDAO and gain some profits. We have many more CFF evaluations on different kinds of contracts, governance contracts, flash loans, airdrops. I would encourage you to have a look at the paper. Finally, in conclusion, we initiated the study of formal behavior. We initiated the formal study of economic behavior of smart contracts through the lens of MEV. We provided definitions of what MEV is and what it means to have secure composition of contracts. We instantiated these definitions into a practical proof system based on formal verification. And developers can use CFF to find bounds on the MEV that their contracts expose, and users can actually use them to study how much MEV their transactions are exposing. With that, I'm happy to take questions.
Thanks. So for questions, you can line up at this microphone or this microphone. I have a question to start. Does this exclude any MEV that comes from off-chain arbitrage? This is the MEV from being able to be the first trade in a block when the price is changed on a centralized exchange?
Yeah, in some sense, the centralized exchange arbitrages, if you're making profits, they would not be captured here.
So it's just like atomic on-chain arbitrage,
yeah.
basically.
Either atomic or it could be multi-block as well.
Right.
But if those profits are actually realized on-chain, then it would reflect in the definitions.
Right. Makes sense.
What's the time frame required for this tooling, and what's your thought on the risks of these systems being built out and across like really efficient compute clusters and people using generalized strategies to automatically formally verify and find MEV strategies?
I couldn't hear that clearly. Could you repeat your question? Sorry.
Oh, sorry. How long does this take to run, and what are your thoughts on the risks of someone scaling a very efficient compute cluster to basically do these methods and search for MEV search for MEV through these methods?
Yeah, I mean, for the second part, I'd answer that first. All of these tools are actually both defensive and offensive in nature. So if you can actually do parallelization and real-time finding of MEV, that can be used by bots. So that's the answer to your second part. For the first part, I actually have some bonus slides. So these are the proving times and the running times of CFF. So on left, you actually see the time it takes to execute the transactions, just execute transactions. So execute 400, roughly 40,000 transactions in around hundreds of seconds. And on the right, you have proving times when you can actually parallelize the proving across many threads. As you can see, this proving is really embarrassingly parallel. There are so many paths that you need to explore, and most of them are independent. So you can actually parallelize this. We did this experiment over a cluster with 80 cores, and the proving times really depend on how many transactions you are exploring. So for a sandwich attack, these transactions would be 3. For more complex attacks, there would be more transactions. But these are the transactions that we explore, 7, 8, and 9. More than 9 transactions, it becomes very hard to prove anything about them.
Awesome, thank you.
Yeah.
Thanks for the great presentation. Could you speak to the possibility of proving whether or not the path dependence has any impact, or affirmatively knowing that certain tests you can run on a state-dependent function will actually deliver the correct results? Can we confirmatively know state dependence and path independence on smart contracts?
So if I understand your question correctly, you're asking whether we can figure out whether some smart contracts have path independence and some smart contracts do not have path independence.
Yes, because that seems particularly relevant in the case of knowing certain results will be delivering false positives, and you'd want to know if they are path dependent or not.
Yeah, so for example, Uniswap, it's well known that it has path independence.
Yeah.
But for other contracts, if they do have path independence, it becomes easier to just slot in that optimization, not explore the reorderings. But for the protocols that we consider, the other protocols do not have path independence. Like for example, Maker, if you're actually doing liquidations, but there's some top up of the collateral before the liquidation, you can't really reorder them. So that's kind of orthogonal to the actual design of the framework.
Okay. Thanks.
Hi there. I guess I'm curious. It sounds like when you're going through, I guess, the tree of the formal verification, you're looking for counterexamples where MEV is over some threshold. How in K are you encoding the idea? Like, how are you encoding that there is some MEV? Is it just that additional transactions can be inserted that lead to some profit, or like how do you encode that in K?
Right. So the tricky bit here is you have to specify some template of the transactions that you want to insert. Right. So once you specify that template, MEV, as you can see here, is actually a function of those input parameters. Right. And then the framework would actually give this function to a solver which says whether this function is less than delta. Right. So you have to specify those templates, and the subtle bit here is basically these insertions can be really arbitrary. So a transaction insertion could be create a new contract, right? Create a new contract X where X is some variable. So those are like intractable insertions, and the framework would just say, I'm timing out, I don't know how many paths to explore, what all to actually do, right? So you have to specify some templates of insertion. So here we explore some kinds of templates for Uniswap, and for Maker, like liquidate some positions, top up some collateral, but it really depends on what transactions you're inserting.
Got it. So when you're talking about the protocols could think about bounds on MEV, it would be bounds of a certain subset of typical forms of MEV, not all MEV.
Yeah, so it will be basically parameterized on the kinds of transactions that you're inserting and the number of transactions that you're inserting. So the bounds that you have, like the MEV is less than delta, that would basically be MEV is less than delta for 9 transactions where these transactions follow this template.
Perfect.
Yeah.
Thank you very much.
I just had a quick question about ways where maybe the user of CFF can like speed up the process. Are there things that you can specify where like, hey, you know, I think that this property should hold, and I'd like CFF to prove it first, so that it like, you know, so that it's faster later, like path independence, for example. Like if you were to input like arbitrary smart contracts into this, or another example is like, oh, you know, I think that like the space of orderings of the transactions is actually much smaller than all permutations. You know, it's maybe, you know, one transaction always has to be first or something. Are those things that can be specified with the system?
Yeah, that's an excellent question. So the question is, can you speed up the verification by actually providing some guidance to the tool? So in this framework, we focused on automating everything and just having the translation from smart contract code to CFF models manual. But with every formal verification, there's some manual component if you want to speed up things. So what you can really do is like specify some invariants of the code. This is a little bit like into the weeds of formal verification, but for example, if you're verifying something like curve finance, and curve finance has loops about actually executing the transaction. So the actual function has some loops inside it. So then in order to reason about those properties, you have to provide some loop invariant to the framework so that it can efficiently find out the execution of those symbolic transactions. If you don't give it the loop invariant, it will just try to figure it out automatically. Will try a lot of things until it finds a right invariant. So yeah, you could provide it some guidance, and that's actually one very promising area of like scaling it by orders of magnitude.
Thanks.
I'm wondering if you have data on the expected MEV with this as you scale the number of transactions, as in when you have 7 transactions versus 8 transactions versus 9 transactions, how much better can you really do with MEV? Is there sense in going to 15 transactions, 20 transactions, et cetera?
Right. I think in the paper we have some graphs on MEV in different types of blocks. So we have 2 kinds of blocks. One is tractable blocks and one is intractable blocks. Tractable blocks have transactions less than 9 and intractable more than that. But we don't really notice a pattern where you have more transactions, you get more MEV, because it really depends on what those transactions are. Like if there's just one transaction that's millions of dollars of trade, that already gives you a lot of MEV. So.
Thank you.
Thanks.
That concludes our session. We're going into a break now, and the next session will start at 3:30.